Welcome to this comprehensive guide on C-sharp exceptions, a truly crucial topic for any aspiring programmer looking to build stable and professional applications. Understanding how to anticipate and manage errors is fundamental to software development, ensuring your programs run smoothly and predictably. Exceptions are essentially signals that something has gone wrong, events that disrupt the normal, intended flow of a program's execution. They indicate that an unexpected or erroneous situation has occurred, which the program cannot handle within its regular logic, requiring special attention. Understanding and handling these exceptions properly is absolutely vital for building robust and reliable applications. Without proper exception management, your programs can crash unexpectedly, leading to data loss, poor user experience, and a general lack of trust in your software. Today, we'll dive deep into four of the most common and frequently encountered C-sharp exceptions: the null reference exception, index out-of-range exception, invalid cast exception, and the broad category of I/O exceptions. Mastering these will significantly improve your debugging and coding skills. Let's begin our journey with the null reference exception, arguably one of the most frequently encountered and often frustrating issues in C-sharp development. This exception is a rite of passage for many new programmers, and understanding it is key to writing stable code. This exception specifically occurs when your code attempts to access a member, such as a method or a property, on a variable that currently holds a null value. Essentially, you're trying to interact with an object that simply doesn't exist in memory at that moment. To clarify, a null value simply means that a reference type variable does not currently refer to any actual object instance in memory. It's like having an empty box where you expect to find an item. There's nothing there to interact with. Consider this common example. If we declare a string variable but fail to explicitly initialize it with a value, it will automatically default to null. This uninitialized state is a common source of null reference exceptions, especially for beginners. Subsequently, attempting to use a property like myString, length on this uninitialized null string variable would immediately throw a null reference exception. The program cannot determine the length of something that doesn't exist, leading to a runtime error. To effectively prevent this common pitfall, it is crucial to always perform a null check before attempting to access any members or properties of an object. This proactive step ensures that you are only interacting with valid, instantiated objects. An if statement is the classic and most straightforward way to ensure your code only proceeds to access members if the object is indeed valid and not null. This conditional guard prevents the exception from ever being thrown. For a more modern and concise approach, C# provides the elegant null conditional operator, denoted by. This operator offers a streamlined way to safely access members, significantly reducing the verbosity of traditional null checks in your code. This powerful operator safely accesses members only if the object on its left side is not null. If the object is null, the entire expression short-circuits and evaluates to null, rather than throwing a null reference exception, making your code much safer. Next, let's delve into another very common C# exception, the index out-of-range exception. This particular error frequently arises when working with collections of data, such as arrays or lists, and is crucial to understand for data manipulation. This exception occurs precisely when you attempt to access an element within an array or any other collection type by using an index that falls outside its predefined, valid boundaries. This means the index is either too small, typically negative, or too large for the collection size. It's fundamental to remember that arrays in C# are zero-indexed. This means the very first element is always located at index 0, and consequently, the last accessible element will be found at an index equal to the array's length minus 1. For example, if you declare an array containing exactly 3 elements, its valid indices will be 0, 1, and 2. Any attempt to access an element using an index outside this specific range will lead to an error. Therefore, attempting to access myArray 3 in an array that only has 3 elements would directly result in an index out-of-range exception. The system cannot find an element at that non-existent position. To reliably prevent this exception, it is imperative to always check the array's or collection's length or count before attempting to access any of its elements. This simple check ensures your index is always within the valid range. A common and highly recommended safe practice is to use a for loop, incorporating array length directly into its condition. This ensures that the loop iterates precisely through all valid indices, from 0 up to length 1, without exceeding boundaries. This particular exception frequently arises from subtle off-by-1 errors in your code or from incorrect loop conditions. For instance, using a less than or equal to operator instead of just less than can easily push your index out of bounds. Therefore, always meticulously double-check your loop boundaries and all index calculations. A small oversight in these areas can lead to frustrating runtime errors that are easily avoidable with careful attention to detail. Now, let's shift our focus to the invalid cast exception, another common error that arises when dealing with type conversions in C#. This exception highlights the importance of understanding C#'s type system and how objects relate to each other. This exception occurs when you attempt to explicitly convert or cast an object from one data type to another, but the underlying runtime type of the object is fundamentally incompatible with the target type. The conversion simply cannot be performed. Casting is a powerful feature that allows you to treat an object of one type as another, but only provided there's a valid inheritance relationship, such as a derived class to a base class, or an implementation relationship, like an object to an interface. For instance, you absolutely cannot directly cast a string like hello to an integer type because there's no inherent conversion path between them. Even if a string contains 123, a direct cast will fail, as it's still a string at its core. Such an explicit cast, where the runtime type is not compatible with the target type, would inevitably throw an invalid cast exception. The C# runtime strictly enforces type safety, preventing erroneous conversions that could lead to unpredictable behavior. To perform a safer cast, C# offers the as operator. This operator attempts the conversion, but crucially, if the cast is invalid or impossible, it returns null instead of throwing an exception, allowing your program to continue gracefully. It is absolutely essential to always check for null immediately after using the as operator. This follow-up check allows you to determine if the cast was successful and to handle cases where the conversion failed without crashing. The as operator provides another robust way to check an object's compatibility with a specific type before you even attempt to cast. It returns a Boolean value, indicating whether the object can be successfully converted to the target type. By using the as operator, you can confidently perform the cast only when it's guaranteed to succeed, thereby completely avoiding the invalid cast exception. This pattern leads to much cleaner and more predictable type conversion logic. It's important to remember the fundamental distinction between value types and reference types when considering casts. Value types often involve boxing and unboxing, while reference types deal with polymorphism, each having different casting implications and behaviors. Finally, let's explore I/O exceptions, a very broad and common category of exceptions directly related to input and output operations. These errors occur when your program tries to interact with external systems or resources, which are often outside its direct control. These exceptions typically occur when your program encounters issues interacting with external resources, such as reading from or writing to files, communicating over network streams, or connecting to databases. These external dependencies introduce potential points of failure. A very common and illustrative example within this category is the file not found exception, which is actually a specific subclass of I/O exception. This particular exception is self-explanatory and frequently encountered in file handling operations. This specific exception happens when your program attempts to access a file at a specified path, but that file simply does not exist on the system. It's a clear indication that the resource your program expects is unavailable. The primary and most fundamental way to handle I/O exceptions, and indeed many other types of exceptions in C#, is by utilizing a try-catch block. This construct is essential for gracefully managing errors that might occur during runtime. The try block is where you place the code that you anticipate might potentially throw an exception. It acts as a monitored section of your program, allowing the runtime to detect and flag any errors that occur within it. The catch block, on the other hand, executes specifically if an exception is thrown within its corresponding try block. This mechanism allows you to intercept the error, log it, display a user-friendly message, or attempt to recover, preventing a program crash. Here's a practical demonstration of how you might effectively handle a file not found exception using the try-catch block. This example illustrates how to wrap potentially problematic file operations to ensure your application remains stable. Beyond try and catch, you can also include an optional finally block. The crucial characteristic of the finally block is that its code always executes, regardless of whether an exception occurred in the try block or was caught. This makes the finally block absolutely ideal for essential cleanup operations, such as closing file streams, releasing database connections, or disposing of other system resources. It guarantees that critical resources are properly managed, preventing leaks. In conclusion, we've thoroughly covered 4 of the most fundamental and frequently encountered C# exceptions: null reference exception, index out-of-range exception, invalid cast exception, and the broad category of I/O exceptions. Each presents unique challenges and solutions. Always remember, defensive programming is the absolute key to writing robust, resilient, and reliable C# applications. It's about anticipating potential problems and building safeguards into your code from the very beginning, rather than reacting to crashes. Therefore, always strive to anticipate potential issues and proactively implement proper exception handling mechanisms throughout your codebase. This foresight will save you countless hours of debugging and improve the overall quality of your software. It's important to use try-catch blocks wisely and judiciously, reserving them primarily for situations where genuine recovery from an error is possible or where logging the exception is crucial for diagnostics. Avoid catching exceptions unnecessarily. By truly mastering these essential exception handling concepts, you will undoubtedly write cleaner, significantly more reliable, and ultimately more user-friendly C# code. Your applications will be more stable, and your users will have a much better experience. Thank you so much for watching this comprehensive guide on C# exceptions. We hope this deep dive has equipped you with the knowledge to write more resilient code. Keep practicing, keep learning, and happy coding on your C# journey.